Okay. So, yeah, my talk now is going to be on coherent structures in wall turbulence, the influence of pressure gradients and roughness, and some insights from transfer entropy. So to motivate this work, things that I'm interested is to study flows, real flows, and it turns out that most flows have perturbations such as bumps. Even you see a vineyard is on a hill, on the desert, on the bottom of the ocean. If you study a flow in a contraction of the wind tunnel, even over aircrafts. So this is like a large-scale roughness element. But also, most turbulent flows occur on rough walls. So here, that's why, for example, the flow past a urban canopy or even due to trees. And we very often idealize this roughness with very ideal two-dimensional roughness. For example, this case where this is a sinusoidal grooves which are uniform in the z direction, so flow is from left to right, or maybe sand grain, or in the case of flow with roughness aligned with the direction of the flow, like riblets, which is a very well-studied roughness. So I want to combine these two and study these roughness effects to the wall turbulence. And the way I do this is this is a channel flow, and I put a large-scale bump in the bottom wall, and on top of that I put the small-scale longitudinal square grooves. And here I will compare the effect of grooves on the flow over the bump, because I will show now that it's very complex. And so this is, here is like a summary of all the regions that show up due to the presence of this large-scale bump. So when you have this bump, you have upstream separation due to mean streamline curvature. But in the case of the smooth bump, these are intermittent. When you add this very simple organized roughness, then this intermittent separation becomes a steady separation. We have a region of flow acceleration in the upstream side of the bump. And what is interesting that we find regions of negative production. We have adverse pressure gradient that leads to flow separation, as you can see in the top. And then there is a shear layer on top of this separation bubble, which is populated by this vertical structure, essentially span-wise rollers. And then there are secondary recirculation regions that get enhanced by the presence of groove, and also other regions of negative production. So first I will do a summary of the flow statistics and the effect of the grooves. So I already mentioned the grooves essentially in the mean streamlines, we don't see there is separation, even though it happens intermittently. But with the grooves, then we obtain a steady separation in the upstream side due to mean streamline curvature, so that is interesting. Also, the mean separation bubble, it is 20% larger with grooves. We will try to explain this in terms of vertical structures, and also there is a secondary recirculation region enhanced. It also happens in the case of the smooth bump with the grooves. Now we have a steady separation, a secondary separation bubble inside the groove. Another interesting result with the presence of a groove in that shear layer, here I'm showing the turbulence intensity, of course picking the shear layer past the bump, but with the presence of grooves, that turbulence intensity is decreased, which is a little bit counterintuitive. Typically, if you have roughness, you would expect turbulence to increase, but here in the shear layer, it is lower, and we'll try to explain that also in terms of vertical structures. And the one interesting point is this region. Here I'm showing now the turbulence kinetic energy production, turbulent production, and of course it has a peak at the shear layer where there is a peak of turbulence. But what we found is there is a region in the flow acceleration part where it is negative, and this is also an interesting phenomena, because if you have negative production, it means there is an energy being transferred from the turbulent to the mean flow. And this is a little bit counterintuitive, because it would mean that it cannot happen everywhere in the flow, because it will contradict the second law of thermodynamics, right? But it can happen locally, and we will try to explain this also in terms of vortical structures, right? And here we show, in terms of, we have some section of why this is happening, and essentially, in terms of flow statistics, if you look at all the contributions, terms that contribute to production in this inhomogeneous flow, we find that there is primarily the streamwise stretching term, or the term from normal stresses, because this term in the flow acceleration region, du dx, is positive, therefore this is the source of this negative production. But we will connect this result from analysis of instantaneous vortical structures. And let's look at this, that figure is not looking good, so we'll show this one. So this is the wall pressure, and here I'm showing the form drag of the bump and the effect of grooves. The initial reason why I was interested in studying these grooves is to control the separation and try to reduce form drag. It was for drag control, but it turns out that when you put this small scale roughness over the bump, there is a larger separation bubble, and also the form drag increased by 20%. However, the skin friction, it is decreased by 5%, but there is a significant increase in the form drag with a overall drag increase of 4%. So grooves actually increase drag anyway, but interestingly because of the form drag of the bump perturbation. And skin friction is in the previous slide, so I will not go there. So now I already mentioned some interesting results from statistics, so I will now talk about vortical structures and how to interpret or try to explain the origin of these observations in terms of coherent structures. So first thing we did is to visualize what vortical structures of the flow in the different regions. So in the upstream side, this is lambda 2. After many visualization, we find that the vortex dipoles are prevalent in this region. And in the case of the shear layer, of course, it is spanwise rollers. But you see, these spanwise rollers are not very smooth. This is a highly turbulent flow. They are very contorted, not really aligned exactly in the z direction, and these are more like turbulent spanwise structures or vortical structures, right? So first, okay, let's try to do some statistics to have a sense of what is happening. And here the two-point correlations of velocity, they just confirm that what is more or less the shape of the structures in the shear layer. We find that in agreement that there is indeed definitely a structure that is in the spanwise direction, aligned in the spanwise direction, and the effect of the grooves is to disrupt the organization in the separation bubble, but it's not giving much information of what is happening in that shear layer and to explain why there is a decrease in turbulence intensity. Correlations of pressure are giving some information. So in the case of grooves, you see the correlation contours extend much more in the spanwise direction. So this is suggesting that somehow grooves are helping the spanwise roller to remain more organized in this flow, because considering that the vortical structure have a local minimum of pressure, but you see the correlation contour extends much more in the spanwise direction. So we may say these are remaining more organized due to the presence of groove, which is a little bit counterintuitive. If we take the profile in the x direction, we see that from the reference point to the next peak, which is an indication of more or less the average separation of spanwise rollers, with the grooves they are farther apart. So the grooves, this is telling that the grooves are modifying the roll-up frequency of the spanwise rollers of the shear layer. Okay? So how to kind of uncover a little bit more information about what is happening in the shear layer. And this method I already introduced earlier today. So I will use this phase log ensemble average. So how to deduce the coherent structure of the flow in the shear layer. And this is a very, I think it was mentioned, it's a very laborious process. But I will try to go in some detail of this, particularly because this is turbulent and not very organized flow. So imagine you have this, you identify the structure features that you care about, but there's not one realization identical to each other. Let's say these stars, you see that I am considering this as a representative, the features that I want to capture, which I think are the important coherent structure of the flow, I want to reduce the structure. If I do a phase log ensemble average without considering the misalignment between the two, this phase average will give me a featureless set of average, right? It will be just like a circle. So in this process, once you identify based on some criteria, in this case, we are using vorticity of the shear layer, peaks of vorticity together with the lambda 2 to guarantee, to have some confirmation that this is a vertical structure, and the vorticity to only capture those structures that are more aligned in the spanwise direction. Today, one thing that I'm considering, based on the discussions today, is actually how to incorporate lutex in the process of eduction. Because you see, now I require two quantities, but maybe lutex, just by one measurement, I can have both of this information, even probably more accurate. So this process of eduction, one thing I'm exploring is how to implement lutex directly and try to reduce the coherent structure. So going back to the process, so one important aspect is once you have decided of these realizations, you have to align them and try to coincide with these features. So when you do this alignment, you are finally obtaining a phase log ensemble average which has the features that you care about this flow. But this is not enough to obtain the coherent structure. You have to go into an iterative process. Once you have a first ensemble, you see there's still some structures that are not quite similar to each other. So you have to go back and discard those structures that do not correlate well with your first ensemble average, such that you can refine this process and actually obtain a more sharper coherent structure by removing those realizations that do not correlate very well with the ensemble average. And this is like an iterative process until there are no more realizations being discarded, and then that's how you decide, okay, this is the coherent structure of the flow. So this is what I did in the shear layer. In the shear layer is a little bit easier because I'm just trying to consider a spanwise structure. So the axis is primarily aligned, but I'm discarding all those that are too, let's say, corrugated or maybe not necessarily aligned with the spanwise direction. So my final eduction is in reality a two-dimensional field, and I'm showing here the eduction at performed at different x locations from the peak of the bump. And you see from this, here I'm showing the coherent streamlines from that phase log ensemble average. And we find that there is this secondary separation bubble. It was not present in the time average, but you see it is characteristic of this flow even in the smooth wall. And in the case of the grooves, what we find is that this secondary separation bubble, it only becomes more prevalent, bigger and stronger based on this phase log ensemble average. So that is, the effect of groove is to increase those secondary recirculation bubbles inside the large separation bubble. And so, and this will affect the overall unsteadiness of the separation bubble. Here I'm now from this phase log ensemble average, where we are showing some additional features of the spanwise rollers. So spanwise rollers are not actually circular, which is not a surprise. This is more like a elliptical vortex, but with a particular inclination with respect to the wall. It has an inclination where the coherent Reynolds shear stress is favoring a positive value. So if we had this inclination, we may even obtain some negative production, which was shown in other papers of our group. But the dominant form of this spanwise roller is this inclined to the wall with this elliptic shade. And we see the effect of the grooves is that the peak of coherent Reynolds shear stress is always lower compared to the smooth wall. So the spanwise rollers, even though they are more organized, they are evolving to be weaker in the case of the grooves. Okay, here is the coherent production, but it's the same result. And another important thing is that we can from the coherent field, if we remove from the total field, we obtain the incoherent part of the flow. And I mentioned already, and this I kind of verified all the results of Fazla, is that the peak of incoherent turbulence production is not in the center of the rotating part of the structure, but on the sides, in front and back. And again, we find that the turbulence due to in the incoherent part of the flow is lower in the case of grooves. And this is like, I took one particular location I make big, but this is pretty much the same information. Is here I'm adding the temperature field. So here I'm also showing the coherent heat flux at one particular X location where we did the deduction of the spanwise rollers. And one interesting thing is, in this highly homogeneous flow, which very often is considered the temperature field analogous to the velocity, here we are trying to explain why the velocity and temperature is not anymore comparable to each other. It's primarily coming from the alignment of the vertical structure. So in a typical flow, in a flat wall, homogeneous flow, you find that the Reynolds shear stress is equal to the heat flux. But when the structure is actually spanwise aligned, not in the streamwise direction, then these two are quite different to each other. So it is that inhomogeneity and difference in heat flux and Reynolds shear stress is mostly by how the vertical structures align in the flow. Okay? So now we did the phase log ensemble average. Here we're showing the 3D view of this phase log ensemble average. Here again, this is lambda 2. And what is happening is that because of the grooves, there are two additional structures, actually a series of counter-rotating vortices that start at the corners of the groove and connect with the spanwise rollers. And these stringwise vortices being induced by the grooves are basically inducing a wavy shear layer, or in other words, inducing a waviness in the spanwise roller. So the total so the shear layer that these spanwise rollers are being rolled up is a much more diffuse shear layer compared to the smooth wall. And this is the part explanation why the turbulence production is actually lower. It's because of that interaction of the stringwise vortices inducing a corrugated shear layer more diffused, and while at the same time is a more diffuse shear layer, but at the same time is helping organize the spanwise roller to remain for a longer time in that shear layer without breaking up. Okay. Now focusing on the coherent structures in the upstream side of the bomb, in this case addressing the negative production aspect. I already mentioned these are prevalent, these dipoles. So if we take an instantaneous structure together with the instantaneous production, in this green is actually identifying regions of negative production. Red and blue, these are lambda 2 structures. So if we find that very often the negative production instantaneously occur in between these dipoles, as you see here. Here is a cross section of this dipole, and the negative production always occur on top of these dipoles. So it is the dipoles in the part responsible for the generation of this negative production you see is happening very often in the flow. And there are many more details I will not go, but is that those dipoles prevalent in the accelerating part, the origin of this negative production. So here that was in instantaneous, but we repeated the process of phase log ensemble average for this, in this case stringwise vortices. It was already mentioned previous speaker that Ginny John work I replicated, but in the case of the flat wall, but together I also did it for the case of the accelerating part where stringwise vortices are also there, but as dipoles. And we find that in the case of coherent velocities are, we compare velocity with temperature, actually they're very similar to each other. So heat flux and momentum flux to the wall in the accelerating part are very similar to each other, but not at the wall. And the reason is because in the case of the flat wall, these are the coherent pressure by phase log ensemble average repeating Ginny Jones' work and Fasle. So there is no pressure gradient on the wall due to the stringwise vortices, but when they are in the region of favorable pressure gradient, they have a strong adverse pressure gradient counterintuitively in the region of favorable pressure gradient due to the wall curvature. And this is what affects the momentum at the wall, but it does not affect the heat flux because in the temperature transport equation or the internal energy equation, there is no, pressure has no role in the transport of internal energy or temperature field. Okay? So now we have gained a lot of information about this flow, but we still want to understand even more the unsteadiness of this flow. I will skip this part. So we already know many aspects of how to explain or attempt to explain in some of the flow statistics, but how to have a deeper understanding of the flow and is we just started to use the concept of transfer entropy, not to be confused with the entropy of thermodynamics. But there is when we have two signals, we can establish the causal relationship between these two signals. So this quantifies the information flow between two time series measuring how much knowing the past of one process reduces the uncertainty about the future of another process. And this way you can establish causal link between these two signals. So this is what we did, and now we want to establish some causal relationships in between the unsteadiness of the separation bubble with, for example, what is happening upstream of the separation bubble, where we dominated by dipoles, while here is dominated by span-wise rollers, and how these two are affecting the reattachment unsteadiness of the separation bubble. Right? So here we're showing that transfer entropy measurement between these 4 points, and we find that most of the effect comes from the upstream side of the bump due to that those dipoles only affect the shear layer, but they don't interact as much with what is happening at point 4 when there is the reattachment point. And this is, we did this for the 3 velocity components, we don't find much difference with each other. But the point 4, so there is an effect of what is happening in the reattachment point. It affects a lot what is happening to the onset of the shear layer. Okay? Now, what is the effect of grooves? Well, it is breaking that notion, because you see the points in the upstream side don't affect at all what is happening in the reattachment point. But when there are grooves, these 2 points, point 1 and point 2, communicate much more with each other. So there is a much greater impact of these dipoles on the unsteadiness of the separation bubble and the reattachment point particularly. So yeah, these are my final remarks. So this is as you saw, we did a lot of work on how to explain some of these flow statistics and results in terms of vertical structures, but we want to obtain some causal relationship between vertical structures in different regions over this bump and the effect of grooves. So we still need a more sophisticated analysis of the causal relationship, particularly to understand a little bit better why we have negative production, so what vertical structure are responsible for negative production, why we have a larger separation bubble, and why the grooves change so much the unsteadiness of the separation bubble. So we will try to improve this analysis and establish those causal relationships. So thank you so much. Any questions?
Thanks, Dr. Kasher.